Linear regression in machine learning, part 2, gradient descent. We are considering the problem of linear regression to approximate the target values y with the help of features x. We are approximating y as wx plus b. The goal is to find the parameters w, which is slope, and b, which is intercept. So we are considering the cost function, least squares criterion, which brings us the best optimal values of w and b. We have already seen that in a simple linear case, this w and b can be computed in a closed form, like analytically with analytical expressions. But it's very instructive to consider how we can find also these parameters by gradient descent, which is much more general way to compute the unknown parameters. Let me explain the basic idea of the gradient descent. Suppose on the left here, in one-dimensional case, we have some function, and let's consider some starting point where this ball is shown. So the derivative in this point, shows the direction of the quickest growth of the function. So if I want to increase the value of the function, yes, I should go in the direction shown by the derivative or gradient. Gradient is the same as derivative, just for the usually for multidimensional sense. But if I want to go in the opposite, if I want to minimize my function, I should go in the opposite direction. Anti-gradient. It's a gradient or derivative with an inverse sign, with a minus sign. So again, the anti-gradient shows the direction of the quickest decreasing of the function. So if I want to minimize the cost function, then here the cost is on the y-axis. I should take some starting point and make a step in the direction of anti-gradient of the derivative with minus sign. Let us see how it works in more detail. So, for example, I have function j, cost function j, depending on parameter theta, and I change at every step of gradient descent. I change this theta in the direction opposite to the gradient of my cost function. Here is the gradient. And I'm making an attempt to go in the opposite direction to the gradient. This weight coefficient alpha is it's called a learning rate. It defines how big will be my step in this direction. So it regulates the convergence of gradient descent. It's very crucial, as we will see, to define proper value of alpha. Okay, let's continue. So let us come back to our problem of minimizing cost function j for linear regression. We must calculate the gradient of cost function g by w, weight coefficient, slope, and by b, intercept. So these expressions are here on the left. On the left are these expressions. We just skipped the constant factor of 2, which comes out after differentiation. So then, in accordance with the gradient descent rule, the update equations for w and b will be as is shown on the right. Yes, we can update w and update b separately. Let us see. Also, this expressions for the update of w and b can be written more in a compact way if we introduce notation. If we introduce notation for the error of parameters estimation. Yes, so how the predicted value differs from the actual value. This error E, if we define this error by E, then the update equations can be written in a more compact way. So W is just updated with the weighted scalar product of features and errors, corresponding errors, and intercept B is updated just by a weighted average value of all errors across the whole training data set. So how we can efficiently implement these expressions? We can use vectorization, yes, for the matter of increasing the speed of computation. We can, at every step, we can calculate the error E, bold gross E, for the whole data set. And then we can efficiently update W as, again, scalar product of X and E of our training array and corresponding errors. W is updated in this way, and B intercept is updated as the average value of this E. Yes, correct. I just wanted to to be sure that the formula is correct. Yes, the B is updated as a with the average value of error. Of course, when error is already 0, for example, W and B, as can be easily seen from these formulas, are not updated. So again, basic steps of gradient descent. We have cost function. We want to minimize it. So we start with some initial approximation for W and B. We keep changing them in the direction opposite to the gradient, and we do this until we reach the point of minimum. For example, the value of gradient, absolute value of gradient, becomes very small, or the W and B on adjacent iterations do not much differ from one another, or we just predefine the number of iterations and stop after this number of iterations is reached. So if we come again to our car small dataset, which we considered in the previous video, of course, to implement gradient descent, this data, both Y and X, miles per gallon, and weight of the car should be scaled. They should be scaled so that the gradient descent can be efficiently implemented. So in these plots, in these graphs, we can see how the gradient descent moves into the direction of the local minimum, and in fact, the global minimum is the situation at every iteration. So before seeing how the learning rate influences, I want to show this example in more detail in Colab. So again, here the formula of the gradient descent on very simple example. For example, let us take function x squared minus 2x, and we can define also its derivative, which will be 2x minus 2. I want to find the minimum of this function. I start with some initial approximation. I define the learning rate, and here are very simple expression to calculate the update of our parameter. So, and then I'm printing at each iteration, the values, so they're slowly moving into the direction of the minimum. I can also plot these points. Yes, the point, yes, obviously x squared minus 2x has a minimum at x equal to 1. And with each iteration, we move closer and closer to this point of minimum. Okay, in the case of our linear regression cost function, also the equations can be written quite straightforwardly. Yes, and at each iteration, we make a prediction, wx plus b. Then we update w, and update w with the mean value of scalar product of error and x, of error and the array of features x. So this is update of w. Then b is updated. Please note that the value of gradient of b, derivative of cost function by b, is computed with the value of W computed on the previous iteration. Yes, here we update the value of B with the gradient of B, which was calculated before. So it does not take into account a newly updated at this iteration value of W. Although it may also converge, I think, but generally the practice is like this. So yes, we can run this code, and we had the same answer for W and B, which was shown in the previous video when we calculated these values analytically by closed form solution. Also, here I wrote this function step by step when the update equations are not vectorized. They're done step by step for each instance of training data. I compute the prediction. I compute accumulate the value of dot product of X and error E, and correspondingly W and B are updated. Cost function is also updated. So I have written it also in the compact form, a gradient descent function, now in the vectorized form. And we can run it starting with some initial approximation, W and B equal, for example, to 100. Yes, we can run it. And we have, this is a graph of the cost function. Even after 200 iterations, it converges. We took the learning rate of 0.5, and we have the same answer. Yes, we have the same answer as before. What is instructive is to consider the influence of learning rate. Here I consider the convergence of gradient descent for different values of alpha learning rate. 0.005, 5,000, 500s, 1/2, 2, and 2 plus very small increasing. So, and we can see that when we take very small alpha, yes, the gradient descent converges slowly. It starts to converge more in more faster way when we increase the alpha, especially for this green line, when green line corresponds to alpha equal to 0.5. But when I already take alpha equal to 2, yes, the cost function doesn't decrease. I don't know why it's so beautiful result that exactly for alpha equal to 2, it doesn't decrease. But when I take the alpha slightly higher than 2, the algorithm already doesn't converge. Algorithm of gradient descent doesn't converge. So it's always very important to select a proper value of learning rate alpha. So here I also compare the computation time for scalar and vector implementation. Yes, the value of scalar implementation of gradient descent takes 3.5, I believe, times more than the vectorized gradient descent implementation. So in linear regression, we can find W and B both by closed form solution and by gradient descent. For gradient descent, again, the scaling of data is essential. So the mean value and should be subtracted, and the values should be divided by the standard deviation. So this data scaling is essential. Otherwise, it doesn't converge. It may not converge. In fact, it doesn't converge in the case of this example. Also, just for the sake of comparison, I show here the implication of sklearn, a linear regression built-in function. Yes, we can also, using our training features and training labels, we can compute the values of parameters W and B, and it provides the same result as we have obtained. Before. This is training and testing points are shown here in blue and red, and the line for what? For testing points is shown. Again, we have average error, resulting error for training data less, which is quite natural, than for testing data. 3.8 and 4.4 respectively. So we have considered the application of gradient descent to the linear regression problem. Here also in this presentation are the plots for different choices of learning rate. So what we have considered by now in these two videos, for linear regression, idea of linear approximation, yes, as we approximate targets or target values y as wx plus b. We introduce loss function and cost function. Loss function is just a square function, but cost function is a mean square for the all data points, for the all training data points. We derive the closed form solution for the linear regression problem, and data scaling, some kind of feature engineering is essential. And we also considered gradient descent with its different aspects, which is very useful, very important alternative, because we cannot always find the closed form solution. Thank you very much for your kind attention.